Thank you very much. I'm very glad to give this talk at this conference and to have the opportunity to be recorded for that. And so today I will talk about mirror symmetry for polynomial singularities. And it's part of my actual research, which is in the general topic, which is on the geometry of the moduli spaces of curves. And to study this geometry of curves over C, I developed some method that I will call some convergence properties in K-theory. So we'll see that at the end of the talk. And so the special topic I will speak about today is the quantum singularity theory. And the main result that I have obtained on this topic, we could call it mirror symmetry. Without concavity. So that's a lot of big words that you probably don't know. So I will explain all of it. K0 theory. What?
K0 theory?
Yes, K0 theory.
Are you going to explain this?
No. But I will talk about this. And so first, I will explain mirror symmetry. That's the first part of my talk. I will spend some time on it, and then more precisely the quantum singularity theory, which is what I worked on during my thesis, and the concavity, which is the most important condition in Gromov-Witten theory and quantum singularity theory, that this is a condition about something to be a vector bundle, and under this condition, things are easier to compute with respect to Gromov-Witten or the quantum singularity theory. And at last, without this condition, I will tell you how to use K-theoretic convergence properties to work without this concavity. And just before going into the main motivation of the subject of this talk, which is mirror symmetry, I just want to mention a few other applications of this general method in K-theory that you will see at the end of the talk. And these applications are, well, you will see some relations with some talks on Monday, for instance. So one application is that some quantum K-theory for singularities. So this will be something related to the talk of Nicolas Perrin, and this is a current work with Yan-Bin Ruan. There are also some relations with something completely different, which are called integrable hierarchies. So this I won't tell you what this is, but this is in the world of the partial differential equations, and this is something completely unrelated to the moduli spaces of curves a priori, and this is joint work with Alexander Buriak and Paolo Rossi. something more geometric about the moduli spaces of curves. Some questions that are asked in these fields are relations in the relations among classes in the moduli space of stable curves with marked points. By classes, I mean some elements of the ring, of the cohomological ring, but we can also take some Chow ring or even the K-0 ring. And at last, something that we can see as a generalization of a direct generalization of this theory is the quantum theory of GIT quotients. And this is something far to be complete, but very interesting. And this is a joint work with Mark Shoemaker. Okay, so that's all about the introduction. Now I want to give you the principal motivation of the quantum singularity theory, which is mirror symmetry. And to explain you what mirror symmetry is, I will start with with an example, which is quite famous. This is the example of the quintic Fermat polynomial. So you take this polynomial of degree 5. This is a homogeneous polynomial in P4 of degree 5 which is homogeneous, and it defines an hypersurface in P4. And as you probably know, the Hodge numbers of this hypersurface, the Hodge diamond, has this form. And as we have seen on Monday, a first incarnation of mirror symmetry is something related to the Hodge diamonds. Precisely, this is the Hodge diamond for X, and mirror symmetry tells you that there exists some other variety Y, such that the Hodge diamond of Y has this form. So you see the symmetry. This column is replaced by this row. And this is called the cohomological mirror symmetry. That's the first step. And so how Y is constructed in this example? This is something quite classical. And you first take the action of mu5. Mu5 is the group of fifth root of unity. And you take the group mu5 to the 4 over mu5. And this group acts on P4. So how it acts? First, mu5 is embedded diagonally into this. And the action of this mu5 to the 4 on P4 is by the diagonal matrix like this. So this is a certain action of a group on P4, and define Y to be the quotient scheme between X and this group. So this, unfortunately, it's not smooth, but there exists some resolution of this, which is Calabi-Yau threefold. Of course, this is also a Calabi-Yau threefold. And this is the mirror, one construction of the mirror. So in particular, this has a Hodge diamond like that. But you have also another way to see the mirror. So not in the category of scheme, but in the category of stacks or Deligne-Mumford stacks. So you just take X, and you take the quotient stack of X by the group G as a stack. And this, we call that a Calabi-Yau orbifold. And as an orbifold, or DM stack, this is a smooth object. And okay, here you have to define some notion of cohomology for orbifolds. And the so-called orbifold cohomology of this space has also this Hodge diamond. So this is the famous example of the quintic, of the Fermat quintic. And this is, as I said, the first step, the cohomological part of mirror symmetry. But there is something more, something deeper in mirror symmetry, as it was said also on Monday, something related with complex deformation of y and something else on x. So introduce this polynomial. So you modify your polynomial Q by this monomial, and you get, by defining yt to be the quotient stack given by the zero locus of qt into P4 and modding out by the group G, you get again some Calabi-Yau smooth orbifold, smooth except from some values of the parameter t, exactly 3 values, and so this is a family over some open subset of P1 is a family of Calabi-Yau 3 orbifolds. Okay, so with this family, I can attach the so-called Picard-Fuchs equation, which is an ordinary differential equation in the operator t over dt. And this is satisfied by all the periods of yt. And more precisely, this is also satisfied by all the volume forms of yt. So the solution of this differential equation are exactly the families of volume forms. And this is a way to encode the deformation of the complex structure of the variety of the family W, family YT. And so the mirror symmetry theorem is that this Picard-Fuchs equation, this same equation, is also satisfied by something, by some structure, some deformation of a structure on X, but which is completely not related with the deformation of the complex structure. So it's also satisfied by something that we call the quantum product on X. And again, maybe it reminds you it's something about the talk of Nicolas Perrin. So what is the quantum product? I want to give you not a precise definition, but a flavor of what the quantum product is. So first, the cohomological product is something that you can see in the following way. Take Ek, a basis of the cohomology of some variety, and consider Ek dual, so the dual basis. Okay, and you want to know what is the intersection product between two classes, two cohomological classes, alpha and beta. What is this in terms of the dual basis? So I want to write some expression like this, and here to put a coefficient. Well, this is quite easy. This is equal to the integral over the space of the product between alpha, beta, and Ek. This is the expression in the dual basis. And this you can see, you can imagine that you have alpha, beta, and ek, and this will count the common intersection of these three classes. This is the idea of this integral. And this intersection, you can also see it as a map from P1, a map of degree 0. So it goes to a point, a map such that the image meets alpha, beta, and ek. And this is the first step. This is just the usual cohomological product. But now let's imagine that you are not interested in the intersection points between alpha, beta, and ek, but you allow you to have no intersection, but to have some rational curve which meets all the classes. So in other words, you're looking now at maps from P1 to X, from P1 to X of a certain degree D, such that the image meets alpha, beta, and ek. And roughly you are going to count the number of such maps into X. So for each degree, you will have some numbers that we call Gromov-Witten invariants of degree D attached to alpha, beta, and ek. And this will be the coefficients in the dual basis of the deformation of the usual product by the parameter, some parameter Q, which remembers the degree of your maps. So when Q equals 0, then you have just the usual product, but you have some deformation of it. And the deformation is encoded also into some differential equation or some local system. Local system is vector bundle with a flat connection. And so the picture that I'm going to write now is what happens. You have over an open subset of P1. Here you have t equals 0. You have a local system given by the Picard-Fuchs equation. And on the other hand, you have here another local system which is given by the deformation of the usual product into the quantum product. So here t is the parameter of this local system is q, but q is not equal to t. You have some mirror transformation. But so the thing is that you also have the local system given by the Gromov-Witten theory of your variety X. And the mirror symmetry theorem is that there is a map, so a mirror map, such that the pullback of this local system here is isomorphic to this local system. And this is, well, this was quite impressive when it was discovered by physicists, because these Picard-Fuchs equations are very well known. You have you have all the solutions of these Picard-Fuchs equations, and with this correspondence, you can compute actually these numbers. Okay, but Picard-Fuchs equation is not only around 0. Okay, you have an equation in t d over dt, but you can do the change of variable s is 1 over t, and you go above t equals infinity. Okay, and here also you have a differential equation given by this change of variable. So this local system is defined over, is not only defined around 0. And here, this was the idea of, well, first the idea of Witten, and then it was established by Fan-Jarvis and Ruan. to give a sense to the analog of Gromov-Witten, but not above 0, but above infinity. So some mirror map here, such that the pullback of this local system by this mirror map coincide with the restriction of the Picard-Fuchs around infinity. So here also you will have some deformation of some quantum thing, some deformation of some cohomology. But what is interesting is that it's not the deformation of the cohomology of a hypersurface, but deformation of the cohomology of a singularity. And by cohomology of a singularity, you can think about the Jacobian ring. So here it's the quantum singularity theory of the polynomial. Well, I will write it W, but for now W is equal to Q. Okay, this is the polynomial defining the hypersurface X. Okay, so this general picture in this example of the quintic Fermat hypersurface has been proved completely by Kyodo and Ruan. But it's also true, well, we know the mirror symmetry for many other cases. We know for all complete intersections X in the projective spaces Pn. Oh, sorry, all Calabi-Yau complete intersection X in projective spaces. But in general, this is not, well, the construction of the mirror is not as easy as here. In particular, here you have the same polynomial on both sides. So here, this is Picard-Fuchs of Yt or Qt. But Qt, or Q in general, is not equal to W. There is some work to do to construct the mirror. In general, W is not Q. And I will not go very far into the details, but the construction that we use in this setting is by Kravitz, Berglund, and Hübsch. And this is, well, there is some recipe to guess the mirror. And then, of course, you have to prove that it verifies the same rules. So if you start, for instance, with Q of this form, well, this is also a polynomial defining a Calabi-Yau threefold of degree 5, an hypersurface of degree 5 in P4, just as the previous example. And you look at the matrix of exponents of this polynomial. That is to say, you start here with a 4, and then a 1. Then the second monomial is also 4, 1, 4, 1, 4, 1, and just the last one is 5. Okay? So this is another candidate for a Calabi-Yau threefold in P4. But here, the polynomial, which will be the mirror, which will define the hypersurface X, is not equal to Q. It's obtained in the following way. You take the transpose of this matrix, and this defines you this polynomial. Okay, and if you take, well, I'm cheating a little bit because there is also something to say about the group G, and I won't tell you about that. But if you take the hypersurface given by this polynomial, by the zero of this polynomial, and modding out by some group, you will have the transpose of the Hodge diamond of this hypersurface. So it's very similar to the first one, but it's another mirror. And to give you how different it is, this is also a Calabi-Yau threefold, but here I should put orbifold, because this is not a homogeneous polynomial. This is a polynomial of this degree in some weighted projective space that I have in my paper, here. Well, it's not very important, but where is it? Yeah. So you have some weights which are not all equal to 1, and this suggests to you that even if you start with a polynomial which is homogeneous, the mirror in general will force you to work with complete intersections or with hypersurfaces in some weighted projective spaces, and not only in Pn. So if you work in weighted projective spaces, well, the mirror symmetry conjecture is open. And well, to be more precise, it's open when the weighted projective space is not Gorenstein. So like in this example, it's not Gorenstein, but this is not the point of this talk. So well, this is, so at 0 you have x to be, x is the hypersurface given by W inside this weighted projective space. And here, at infinity, you will have the quantum singularity theory of the polynomial W. So it's a different polynomial, but it's the same as the one here, but not the same as the one here. That these two are related? Yeah, always. Yeah, yeah, exactly. Yeah, that's a very strong relations between Gromov-Witten theory and the quantum singularity theory. And it's not just by chance, but this I cannot detail that. But these two models are in fact coming from the same. These are two GIT quotients of some common model. So yeah, this here you have some GIT theory to go, which tells you exactly what is X and what is W. And so in particular, the Jacobi ring of W it has the same dimension than the cohomology of X, and they are both they have both a Hodge diamond, which is inverse of this one. So what I want to say now, before going into the geometric ideas of this theory, is okay. So this picture is open in general in weighted projective spaces. And this is because, as I mentioned, because of the lack of concavity condition, which I will explain in a moment. And what I have done is to prove the mirror symmetry part of this whole picture on this side for some singularities, for some W, which for which the concavity condition is not true. And this part is completely unknown. So now I will go on the quantum singularity theory. And well, so I want to describe you what is the geometry problem, the geometric problem that is studied by this theory. So in Gromov-Witten theory, the problem was to look at stable maps to your target space, and with some conditions, or some intersection conditions. Here, it's a bit different. So let me start with a polynomial of a specific type, which is of the same type as the one there. So you have several variables. We defined also some hypersurface in some weighted projective space, so certain degree D, and this is in a weighted projective space with weights W1, Wn, so it has some quasi-homogeneous properties. And starting with this, you construct the following moduli space. This moduli space classifies the families of curves over a base S with some marked points and with some line bundles. You have as many line bundles as the number of variables in your original polynomial. And then you impose some conditions on these line bundles. For any monomial of W, you will have an algebraic condition, which you can see has the same form as the monomial itself. So this is required to be isomorphic to the log canonical line bundle on C. So the canonical line bundle on C twisted by the divisor of the marked point that I will denote by sigma. And of course, just the last monomial, sorry, I forgot the last monomial. The last monomial is a bit different. Okay, so you have line bundles on a family of curves with some algebraic conditions which are given by your original polynomial. And here I have a gamma, a vector gamma. Gamma is gamma 1 to gamma n. I will tell you in a minute what this is. This is as many as the number of marked points. And this comes from the fact that to compactify this space, to have a proper space, you need to allow a little more than just stable curves. So you allow, of course, curves with nodal singularities, but you allow more. You have indeed an orbifold structure on each marked point and on each node, an action of the group of R-root of unity, where R is this number. And on this curve, you have your line bundle everywhere. And a line bundle over a marked point, which is an orbifold marked point, which has an action of the group mu R. So let's say this is the marked point sigma I. It has an action of mu R. This is the line bundle Lj at sigma I. This is equivalent to an element of the group mu R. This is equivalent to giving us an action of this group on this fiber. So this gamma I are just the type of the line bundles at each marked point. So there are matrices, diagonal matrices, where each entry is a R-root of unity, and you specify the action of the group on each line bundle on each marked point. And this is a proper Deligne-Mumford stack with a map to MGN bar, the moduli space of stable curves, just by forgetting the line bundles and the orbifold structures on the curves. Where you have also some conditions on this type, on this action. I won't tell you all the conditions, but for instance, this matrix leaves the polynomial W invariant. And this is just because of these relations and the fact that the log canonical line bundle has a trivial action of the group on each marked point. So you can look that from this, then the gamma I, the matrix, is leaving W invariant. So this is the geometric problem asked by the quantum singularity theory. To look at family of curves with line bundles. So in a very specific case where the polynomial has just one variable, which is x to the r, then you have just one line bundle over the curves, such that the r power of the line bundle is the log canonical line bundle. And this is called r-spin curves. Maybe you know the word spin curves, which is the particular case of x square. So the goal now is to construct a geometric class in the cohomology of this moduli space. What I mean by geometric, well, you will see in a minute, it's a class which takes into account the geometry of the problem, so which takes into account the line bundle Li's, for instance. Because this moduli space is smooth, so you can take, if you want, the fundamental class and do intersection theory on this moduli space with the fundamental class. But here, the quantum singularity theory of W is in fact the intersection theory on this moduli space, where you intersect not against the fundamental class, but against this class that I will tell about. So now is the most important property of concavity, which is that for all j and for every geometric point, your line bundles, they have no global sections. So this is a very important condition and very restrictive, and it implies by Riemann-Roch theorem that the first higher push forward of the Lj is a vector bundle on the moduli space. Because each fiber, H1, has constant rank. And then this geometric class will be nothing but the top chain class, or the Euler class, of these vector bundles. So this thing will be the class that we will integrate on to obtain some the quantum singularity theory. First it was called, it comes, well, in Gromov-Witten theory, you have the same condition, which is called convexity, and which is the condition that the H1 of some line bundle is 0. And then you have also a vector bundle, and then you know exactly what the class you're looking for is. So here it's just, well, it's just a dual version, and so it does not answer your question. I don't know why it's called convexity for Gromov-Witten theory. But well, I'm sorry, I don't know. So the problem now is when you don't have this hypothesis, then you will not have a vector bundle given by the R1. But you want something, some class which is geometric in the sense that it has to do with the higher push forwards of the Lj. So you want something like the top chain class or Euler class of the full higher push forward. So this top chain class of this will be this geometric class that I will denote by C of W, and this is a class in my on my moduli space. But this is the main problem, because the top chain class is not invertible. The top chain class has several properties. First, it's multiplicative. Second, it's pure degree. So let's say you start with a top chain class which is of degree 2. Then the top chain class of the opposite element in the K-theory will be of degree -2. And that's a problem, to have a cohomological degree -2. So this is the main problem. The top chain class is not defined in K-theory, just defined on vector bundles. And well, these are the two challenges. Well, here are the two challenges which were answered by Polychuk and Van Top to construct this class. First, they need to use the data of the polynomial W. The fact that these higher push forwards are not just any element in K-theory, but are coming from line bundles which have some relations between them is very important. Without that, it's not possible to give a sense of a top chain class of this element. And second, it's quite subtle, but it's also a huge part of Polychuk Van Top work, is that the line bundles on each marked points, the global sections, you will say that it's dimension 1, right? This is the usual case. But here you are above an orbifold point. So the global sections, by definition, have to be invariant under the action of mu r. So to be invariant when the action is non-trivial means that you need to be 0. So this group is 0 if the action of mu r is non-trivial. And if the action of mu r is trivial, then this is the usual case where the fiber of Lj, where the global section at the point sigma I is dimension 1. And this dichotomy is very interesting. This in particular makes things very much harder in the Polychuk Van Top work. And this dichotomy is something really related to the dichotomy in Gromov-Witten theory between ambient classes, the classes in the cohomology of the hypersurface coming from the weighted projective space, and the primitive part of the cohomology. And in Gromov-Witten theory, it's not known how to compute the primitive part of the primitive part of the cohomology. It's not known. And here also you have problems with this case. But this was answered by Polychuk and Van Top, and they use the notion of matrix factorizations. So the construction of this geometric class is quite well understood, but I will just give you in the last 5 minutes an alternative definition of this class. An alternative definition which is closer to the original idea that it's something like an extension of the top chain class. So this is an alternative definition. For you, this will be the only one. But at last, I have the theorem that it's the same as Polish-Van Trapp definition. And this uses the K-theory. So if you think about the top chain class in terms of K-theory, so you're asking the following question. Let V be a vector bundle on space S, and you want to write the top chain class of V in terms of in the language of K-theory. So in K-theory you have something very good, which is a lambda structure. Lambda T of V, by definition, it's the polynomial whose coefficients are the exterior powers of V. So this is a polynomial in T. The degree is the rank of V. And the top chain class is the chain character of lambda minus 1 of V dual times the top class of V. This is a famous formula. It's not very hard to prove. And well, with this formula, well, for now we have nothing more than before. But in K-theory, you have the notion of lambda structure even on elements which are not vector bundles. In other words, for minus a vector bundle, you have also this lambda structure, which means that you can invert this formula. And if you invert this formula, well, the inverse of the exterior powers is the alternating sum of the symmetric powers of V. So this time, this is not a polynomial anymore, but this is a formal power series in T. So this lambda structure you can invert. This top chain class you cannot. But what you can define is the following characteristic class defined in the whole K-theory. Given by, so to the image of B minus A, where B and A are vector bundles, you attach the chain character of lambda minus T B dual over lambda minus T A dual, and then you multiply by third class of B over third class of A. Third class is invertible, there are no problems with that. And you have something which looks very much like a generalization of the top chain class, well, a generalization of this formula in K-theory. Unfortunately, this will have, in general, no chance to converge when T tends to 1, explicitly because the top chain class is not invertible. So this is just a formal power series in T with a radius of convergence of 1. And so in general, you cannot say a lot about that. But I have proved some theorem, so I will give you just an example. If you start with a family of curves and with a line bundle, which is the R-root of the canonical line bundle twisted by an effective divisor, then, so this means that L to the R and O of D are dual in the sense of Serre. And you have these relations, the fact that the lambda structure of the push forwards of L and of O of D is a polynomial in T. So because the L to the R is Serre dual to O of D, you have this times this is a polynomial. Because L to the R is a R power of L, you have t to the 1 and t to the minus r here. So this you can see as as properties of third duality and taking R-root, the R-root constructions. Once you take the push forwards using the lambda structure. So, to emphasize this, just this piece is not convergent. It's a series in T. Just this piece is not convergent. It's a series in T. But the product of the two will produce some vanishing in the K-theory ring, such that this is at last a polynomial. And I finish with my theorem about the quantum singularity theory, which is that so in genus 0, if you start with a polynomial as I'm talking about since the beginning, so with W, and you have the line bundles L1, L2 until Ln. You define Lj prime to be either to be Lj twisted by the marked points. This is when L minus j is even, or this is Lj if L minus j is odd. So 1 over 2 line bundles is twisted by the marked points. This is very weird, but this comes directly from the matrix factorization that I didn't talk about. So that I cannot explain. But if you take these line bundles, then the product of the higher push forwards element of these line bundles with variables tj, which are not all equal to the same variable, but just as here there are some powers. So precisely t1 to the a1, t2 is 1, t2 to the a2, t3 is 1, etc. So for each monomial, you have this condition. This, when t1 tends to 1, this converges. And okay. So definition, so theorem, this converges. Definition, I denote by CW, so the geometric class I'm looking for, the limit. And second theorem, this is compatible with the definition of Polyshuk and Weintraub. Thank you very much.